Hello, today I will be sharing a reduction from the independent set problem to the vertex cover problem. Here are the table of contents. I'll first go over the purpose, the problems themselves, a reduction from the independent set to the vertex cover, a reduction from the vertex cover to the independent set, some full examples, and proofs of NP completeness, and a conclusion. Purpose will explain what it means to reduce the independent set problem to the vertex cover problem, and vice versa. Reduction is solving a problem by using a black box solution to solve another problem. The reason why reduction from an independent set to a vertex cover is important is because it shows that the vertex cover problem is at least as difficult as the independent set problem, and vice versa. If there indeed exists a polynomial solution to one problem, then there will exist a solution to the other. Now we'll go over the problems individually. The first being the independent set. It is defined as a set of vertices X that is a subset of the total amount of vertices in a graph G, such that the total amount of edges has no edges between two vertices in X. This means that no two adjacent vertices can share an edge between them and be in an independent set at the same time. The decision version of this problem is, given a graph G and an integer k, does G have an independent set of size k? And we want to find the greatest number of vertices, which is the maximum value of k. We can also prove that this problem is an NP by saying, if we are given the independent set of size k as a certificate to be verified, we can write a polynomial time algorithm to check that G doesn't have any edges between any pair of vertices. And we'll go more into this later. As we can see in the image, a valid independent set can consist of vertices 1, 4, and 5, and an invalid set could be vertices 1, 2, and 7, because 1 and 2 share an edge between them. Next, we'll go over the vertex cover problem. It is defined as, within a graph G, a set of vertices X that is a subset of the total amount of vertices, such that the edge in the set E, which is a total amount of edges, U is in the set X, or V is in the set X, or both. This essentially boils down to the definition of a set of vertices that covers all the edges in a graph. We can see on the right side in the image, the orange vertices cover all the edges in the graph because all of the edges include at least one of the orange vertices. The decision version of this problem is, given a graph G with vertices and edges, and an integer k that is greater than or equal to 0, does G have a vertex cover of size k? And we want to find the minimum number of vertices and the minimum value of k. If we are given the vertex cover of size k as a certificate to be verified, we can write a polynomial time algorithm to mark edges in that vertex cover and check if all edges in the graph are marked. And we'll go deeper into this as well. Next, we'll go into reducing the independent set to the vertex cover problem. Given a black box solution that solves the independent set problem, how can we use the solution to solve the vertex cover problem? We know that no edges are in between a pair of vertices in an independent set, and this is by definition. This means that every edge has at least one vertex not in the independent set. If an edge had two vertices in the independent set, the vertex cover wouldn't be able to cover all edges, and this would be a contradiction in itself. And now, the vertices that are not in the independent set make up the vertex cover, and we can reach the conclusion that a vertex cover is found in a graph if and only if there exists an independent set in the graph. Here we have a function which essentially states that the number of vertices in the vertex cover is the total number of vertices minus the number of vertices in the independent set. And as you can see in the image, a complement of the vertex cover is the independent set itself. We can see that the vertex cover has 3 vertices included in a total amount of vertices 5 in the graph, whereas the independent set has 2 vertices. If we add them together, they would add up to the total amount of vertices in the graph, which is 5. A yes instance of the independent set corresponds to a yes instance of the vertex cover, because if there is an independent set in the graph, the complement vertices are in the vertex cover. A no instance of the independent set becomes a no instance of the vertex cover, because if a graph does not have an independent set, it would not have a vertex cover. And now we're going to go deeper into the time complexity of this. This reduction takes linear time, because if the independent set is already given, all that is needed is to go through the graph and check if the vertex is not part of the independent set. This is assuming that these vertices are marked. If they are not marked, if we only know the size k in the independent set, we just need to count the total amount of vertices in the graph and subtract k to find the number of vertices in the vertex cover. And this is why it only takes linear time, and therefore a proof of P. Now we'll reduce the vertex cover problem to the independent set problem. Given a black box solution that covers the vertex cover problem, how can we use the solution to solve the independent set problem? Each edge in the graph must have at least one vertex in the vertex cover. And this is by definition, because the vertex cover covers all edges. This means that every edge has at least one vertex in the vertex cover. If an edge had no vertices in the vertex cover, that would mean the independent set has an edge between 2 vertices, and this is contradictory to what an independent set is. And these vertices make an independent set. And so we can reach the conclusion that an independent set is found in a graph if and only if there exists a vertex cover in the graph. And this function is exactly the same as before, just reversed. The number of vertices in the independent set is the total number of vertices minus the number of vertices in the vertex cover. And the image is exactly the same as before. A yes instance of the vertex cover corresponds to the yes instance of the independent set, because if there is a vertex cover in the graph, the complement vertices are in the independent set. A no instance of the vertex cover becomes a no instance of the independent set, because if a graph does not have a vertex cover, it would not have an independent set. This reduction also takes linear time, for the same exact reason. If the vertex cover was already marked and given, we would just need to traverse through the graph and check if the vertex is part of the vertex cover. If it's not, it would belong in an independent set. If they are not marked, and we only know the number of vertices k in the vertex cover, we just need to count the number of total vertices and subtract this k to find the number of vertices in the independent set. Now we'll go over some examples of the reduction. Here's the first one. I've already circled the independent set vertices. We can see that the vertices C and the vertice B are 2 vertices that are not connected by an edge. And these are, this is one possibility of an independent set. Another possibility could include A and E, since they are not connected together. But we know that no matter what, this graph only has an independent set of size 2. If we use the information we had from before, this means that the vertex cover size is then 3, because the amount of vertices in the graph in total is 5, minus the number of vertices in the independent set 2 is 3. And we see that this is correct. because we see that each green circle that is in the vertex cover covers each edge. If we go from A, it covers the edge AB, AC, AD. The vertex D covers DB and DC. And the vertex E covers the edge EB. And this will cover each edge in the graph. And this is exactly the same thing. And we can see that they're equivalent and complements of each other. Here's another example. And this time we'll go from the vertex cover to the independent set. Now, this graph has a vertex cover, and its size is 5. We can see that the vertex 1 covers 1 to 3 and 1 to 2. The vertex 4 covers 4 to 3, 4 to 8, and 4 to 9. The vertex 9 covers 9 to 8 and 9 to 6. The vertex 7 covers 7 to 6 and 7 to 5. The vertex 5 covers 5 to 2 and 5 to 6. And this is the minimum amount of vertices needed to cover all of these edges. Now, we can assume that the independent set size is then 4, because 9 minus 5 is 4. And yes, this is correct. The independent set is size 4. Only these 4 vertices are not connected by an edge together. For example, if we included this 9 vertices in the independent set, it would not work because it is connected to 6 and 8. And that goes along with every single vertice in this graph that is not already part of the independent set we have here. So again, we see that the sizes are complements of each other. And now we'll go over the proofs of NP completeness and the final conclusion. In order to prove that a problem is NP complete, it must be NP and in NP hard. We have already proved that both the independent set and vertex cover are in NP. We created decision problems, we created certificates, and we showed that these certificates are in polynomial time. Therefore, they meet the criteria to be in NP. And we have already also proved that both of these problems are NP hard. Since we can assume that an independent set is already known to be NP hard, and we reduced it to the vertex cover, the vertex cover is also in NP hard, and vice versa. Therefore, both the independent set and vertex cover have fulfilled the criteria and are both in NP complete. Finally, now we can say that the independent set problem and the vertex cover problem are both equal-ended because they can reduce to one another. They both have polynomial time certificates, and solving one is at least as hard as solving the other through reduction. Therefore, they are both NP complete and equivalent. Thank you.